Now that we know the 5 basic shapes of linear, trigonal plane, tetrahedron, trigonal bipyramid, and octahedron, we're ready to start replacing some of those legs with lone pairs. And in this part 2 of our lesson series, we're going to go up to where we have 4 electron pairs and start replacing some of those legs with lone pairs instead of atoms. Okay? So if the central atom has lone pairs in it, okay, we've got lone pairs on that central atom, they are going to also take up legs in that electron pair arrangement, or what we called electron geometry. Okay, so we have to keep a few things in mind as we decide which one of those legs on our geometry is going to be going to house those lone pairs. So we're going to keep in mind that lone pairs, because of the way they're not surrounding a nucleus but are out away, are big and fluffy, and they need more room. And if you have a lone pair and another lone pair, they're going to need to get a little bit further apart than a lone pair with a bonded pair. And the bonded pair with a bonded pair, that's what BP and BP stands for, bonded pair to a bonded pair, they won't need as much room, so the repulsion is not as great. So lone pair repulsion is the biggest repulsion. Bonded pair repulsion is not as competitive. It does not have to push apart as hard as a lone pair does. Because of that deal, okay, this is the reality of what it causes. We want to make sure we give lone pairs the spots that have the most room. And so we're going to see how we examine that and decide on that. Let's give lone pairs a spot with the most room, and if we have more than one lone pair, we need to get them as far apart from each other as we can get them. Okay? Also, the thing that it's going to do is it's going to change those bond angles. So when we learned that a tetrahedron was 109.5 degrees, we're going to learn that putting lone pairs in changes that. Now, I'm not going to make you memorize new bond angles, but I am going to make you know that they do change, and we'll talk about how that happens and what I expect you to answer if you were asked for a bond angle. So let's go through some examples. Before we do the examples, there is a table in your book, and it's a table at 10.1 intro, but you know, who knows what book you're using in the future. So I left that blank there. You might want to find that table. What this table does is a summary of all the possible geometries for all these different things that we're going to look at. And some people want to go to that table and just memorize it. You know me. I hate memorizing things, and I hate for you to memorizing things, because memorizing things doesn't make you any smarter. It just means you stuff more stuff in your brain. I want you to understand why these names are the names they are. Be able to come up with those names based upon doing the work that we're going to do, okay? But this table is a good summary of all of those so that you can become familiar with what are my names that I get to choose from? What am I going to be looking for in terms of names, okay? So it is a summary of these. So you're going to do all the stuff that we've done up to this point, all the way up to it, but we're going to start giving them different names for their geometry, okay? So let's give those different names. Let's do some examples. NO2- is our first example. So nitrogen is a central atom. It has an oxygen on either side, okay? We count valence electrons. Nitrogen has 5. Each oxygen has 6, and there's 2 of them. I have 1 more for that negative charge that we see there. Okay, can you see that negative charge? It's tiny. All right, so we have 1 more for that, and that's going to give me 18 electrons to work with. This is kind of a review of doing Lewis structures. We start with single bonds, 2, 4. Then we go to external atoms, the terminal ones, 2, 4, 6, 8, 10, 12, 14, 16, 18, and we have to stop. But nitrogen is not a happy camper there. It doesn't have enough, it does not have 8. So we shift from the terminal into the middle. So I want to take those 2 there and put them here instead. And now we have a Lewis structure. And if it was a really good, we were good students, we'd do that. But you know, that's not necessary for us to do the next step. Now we need to count the electron groups. Electron groups, which I call legs, okay? Legs around that central atom. We count the number of atoms, not the number of bonds, okay? It has got nothing to do with a double bond. You count the number of atoms, because those have to stay together. We'll have 2 atoms, and I have that. and then I count the number of lone pair on that center, number of pairs, not how many electrons, but the number of pairs. So look at that. I've come up with the number 3 for my legs. Okay? Bonded atoms, lone pairs, 3. So now we know what 3 things trying to get as far apart from each other as they can go looks like. So we have a nitrogen in the middle, and we have 3 things trying to get as far apart from each other as they possibly can go. And that was a 120-degree bond angle that we saw, and that electron arrangement, we can call it many things, and different books call it different things, okay? Electron geometry, electron arrangement, I've heard it called, and that's what I called it here, EPA, for electron pair arrangement. What we need to understand is that this is not the final molecular geometry, but this is the starting point. All of these we would call trigonal, 3 things, planar. 3 things trying to get as far apart from each other as they possibly can go. That's what we have. So let me pull up our trigonal plane. Here it is. But all of them are no longer atoms. We have to replace one of these with lone pair, or think about it as 2 electrons sticking out with no atom, okay? So one of these I need to take off as an atom, so it can just be sitting there as a lone pair. So I'll leave the yellow sitting there representing the lone pair. The question is, of these 3, we have to give the lone pair the biggest spot, okay? Do any of these have a bigger roomier spot than in the others? No, they're all equivalent. So it doesn't matter which one I take off. So I'm going to take this one off right here. When I take this one off, okay, the lone pairs are still holding their spot. Okay, but there's no atom here, is there? So what I'm going to do is I'm going to let this represent, and I'm going to just kind of draw a big fluffy space. That's my lone pair. I'm going to put 2 electrons there representing my lone pair. Looks like a little space alien, doesn't it? That's my lone pair. And then I have 2 of the legs with the oxygen atoms, okay? The name of the electron arrangement, or the electron geometry, is called a trigonal planar, but the name of the geometry changes. So the molecular geometry, sometimes we say, what is its shape? What is the molecular shape, molecular geometry? We only look at the atoms to define that. So you would ignore the lone pair, only look at the atoms, and then there is a name that emerges from just the atoms. So I have these 3 atoms. They're not in a straight line. If they were in a straight line, it'd be called linear. When they're not in the straight line, it's called bent. Now I've seen some books try to make this sound sophisticated, and they call it angular, okay? We won't call it angular, we'll call it bent. It is 3 things that are not straight, so it is bent. Now what about the bond angle? Instead of using a bond angle of 120 degrees, what happens is this lone pair needs more room than these guys need with each other. So it pushes these together a little bit more. So this bond angle between atoms, we would say it's less than 120 degrees. We don't know how much less, okay? A few degrees less, it pushes it in, and so this between the lone pairs and the oxygen, that part is now a little bit greater than 120 degrees. But when we talk about bond angles, we're talking about between atoms. We don't define this, so I won't ask you what's the bond angle between the lone pair and the oxygen. So I'll never ask you that question. I will ask you the question, what's the bond angle between the atoms? And then you would say, well, it's based upon the trigonal plane. And the trigonal plane was 120, so this is going to be less than 120. So here are the questions that could be asked. What is the electron arrangement? It's called trigonal planar. What is the molecular geometry, or the molecular shape? It's called bent. What's the bond angle? Less than 120 degrees. Okay? So based upon a trigonal plane, that's my only choice. It's either a trigonal plane because there's atoms at each one of those locations, like this, or it is bent, because if we take one of these other legs and turn it into a lone pair instead, which we could do a geometry for, we just have 2 atoms, and 2 atoms are always linear. There's no other choice. Okay, so don't do all of this work if you have 2 atoms and they say, what's the geometry? 2 atoms, always straight line, linear between them. Okay, let's go to the next one. What we got next? NH3. All right, so we're going to do a Lewis structure because that's always where we start for NH3. We have nitrogen surrounded by 3 hydrogens. I'm just going to jump straight to the Lewis structure. Straight to the Lewis structure, it looks like this. Now we're going to count our legs, okay? Counting the legs or the electron groups. We have 3 atoms, 1, 2, 3, plus a lone pair, 4. So we have a magic number of 4. 4 legs. 4 legs trying to get as far apart from each other as they possibly can go. What we learned about that is that that's called a tetrahedron. So I'm going to draw my 4 legs. One's in the plane, the other one is in the plane, one is coming out at you a little bit, and one is going back behind it. And we have 3 of them with hydrogen, and one of them is a lone pair, and we have to decide which one's which. So let's look at a tetrahedron for a little bit. Okay? As we look at this shape, is there any one place that's roomier than the others? Okay? Or are they all look exactly the same? No matter how I hold it, this thing doesn't look any different. No matter which one I put at the top, which 3 I put down at the bottom, whether I hold it like this, it doesn't matter. All of them have exactly the same room. Okay? All of them are equivalent. So I want to take one of them and pull off the atom. There we go. And then I'm going to hold it like this. So the 3 that are atoms are down at the bottom, and the one that's a lone pair I'm going to put at the top. Okay? It doesn't matter. I could hold it however I wanted to, but I'm going to choose to hold it like this. So I'm going to go over there on the light board and I'm going to draw what I see here the way I'm holding it. What do I have at the top? I have the lone pair. So I'm going to put the lone pair up here. So it's a big fluffy space. It needs a lot of room. And then the other 3 down here are going to be my hydrogen atoms. Okay? Now, what was the name of the electron geometry? Just the electrons, how they arrange themselves. The electron geometry is called a tetrahedron. That's what we learned before. This is a tetrahedron geometry, electron geometry, where all electrons are being considered. Now we're ready to do what is the molecular geometry. Subtle difference, right? This is all the electron groups, all the legs of 4 tetrahedron. Now when we get to this part, we're only going to be looking at the atoms. So we kind of ignore this part right here. And we look at just what we see down here. So we're ignoring this, and we're only looking at the atoms, and we give it a name. So I'm going to totally ignore it by pulling it off altogether. Now those lone pairs are sitting here and holding this shape. But let's give this thing a name. This has got a name. It is a little pyramid, isn't it? What kind of base does this pyramid have? It has a triangular base. Okay? So what we call this geometry, it's called a trigonal pyramid, or a trigonal pyramidal geometry. I don't know if you can read that. Let me see if I can get my pen dang. Pyramid. Okay, so we have a trigonal pyramid as the name of the geometry. Let's talk about bond angles. For a tetrahedron, we learned that the bond angle was 109.5. Because of this lone pair, the bond angle is less than 109.5. Okay, so with this geometry, we have other choices, okay? We had with our tetrahedron, which I'll put the leg back in here, you know, we have our tetrahedron. We could have 1 lone pair, we could have 2 lone pairs. If we had 3 lone pairs, we just have 2 atoms and we have a linear molecule. So we're going to consider the next one as soon as I get my board erased. So now we're ready to do water, okay? So we're going to work our way through doing the molecular geometry of water. We'll start with the Lewis structure. The Lewis structure looks like this. And I have seen time and time and time again students who say that is a linear molecule, because as soon as they draw a Lewis structure, it looks linear to them, and so they choose linear as an answer. You can never know the geometry by looking at the Lewis structure only, because you could draw it any kind of ways. It's just a 2-dimensional representation. You have to go through these steps, okay? So that we're going to count those legs. Remember, my legs is what I call those electron groups. You count bonded atoms, there's 2. Lone pairs, 2 more. 2 plus 2 is 4. I have 4 legs trying to get as far apart from each other as they possibly can go. 4 legs getting as far apart from each other as they possibly can go is oxygen in the middle, And then my 4 legs is the shape of a tetrahedron. Okay? So the electron arrangement or the electron geometry, electron arrangement, electron pair arrangement, those are the different ways it could be stated. I say this because you're going to see it all kinds of different ways. But the focus is on what all those electrons are doing. This is all a tetrahedron. So we have 4 legs. 2 of them are lone pairs, 2 of them are hydrogens trying to get as far apart from each other as they possibly can go. So we're going to pick up the tetrahedron after I drop it. Then I won't pick it up. All right, so here's my tetrahedron where I've got atoms on each location. But I know that 2 of these are lone pairs, so we have to decide which 2. Start with the first one. Does it matter? All 4 legs are equal, so I'm going to take one off. So I take this one off and I have these 3 down here now with this one up there, and I have to choose the next one. Now the next one needs to go into the location that has the most space. Is there any difference? Are all of these the same distance away from that lone pair? Sure they are. So it doesn't matter which one I take. So I'm going to take this one here. Okay. Now what do I have? I have the lone pairs and I have the atoms. When I do the geometry, what I call the molecular geometry, I look at just the atoms. Okay? Now before we give it a name, let's put it together here. 2 of these legs, okay, I'll do it this way. 2 of these legs are atoms. 2 of these legs are lone pairs. So I will draw them as big fluffy spaces at holding the pair of electrons. Now we only look at the atoms. We have seen this name before. This is not something new to memorize. 3 atoms that are not in a straight line, they are not linear. 3 atoms that are not in a straight line have a name. What is it called? It is bent. Now this bent is different than the other bent because it's got a different bond angle. This is less than 109.5 because it was based upon a tetrahedron that has 109.5 degree bond angles. But because these lone pairs need more room, they will push on that and shorten it a little bit, so it's less than 109.5. This is even less than the previous one, which was a Trigonal Pyramid. Okay? But these lone pairs will push even more on these and bring it down a little bit more. So that is a 4 legs, 2 of them are lone pairs, 2 of them are atoms. It will always be bent. Now would I want you to memorize that? I don't want you to look at this and memorize that word. You can. That is a way to do this. But memorizing does not make you smarter. Makes you answer questions on tests, sure. And if that's all you care about, that's one thing. So you can memorize, when I draw this and I have 2 atoms and 2 lone pairs, it's bent, I've memorized my angle. Or you can take a little bit of time and say, why is it bent? I have 4 legs, let me draw them. 2 of them are lone pairs, 2 of them are atoms. Look only at the atoms. What's the name of that shape? Well, that is a bent shape. It is your choice which way you go. I would certainly rather see you understand why it's called bent than memorize that it is bent. So let's look at images of this. Oh no, we have, oh, I don't want to do that one again. I don't want to do that one again. I've done all those. Okay, so let's look at the screen here and let's see those 3 geometries all based upon the same electron arrangement. They're all based upon the tetrahedron. If all of them are atoms, 1, 2, 3, 4, we call this one a tetrahedron. And the bond angle we see right there, 109.5. If one of those legs was a lone pair, and we're not seeing it drawn in, but there's a pair of electrons taking up one of those legs, we only look at the atoms, and this one is called a trigonal pyramid. Okay? And then if 2 of them are lone pairs, which I'm not going to draw them in, but 2 of them are lone pairs, this is the one we just did, it's bent. All right, that's the name of it. It's bent, and the bond angle, notice how it shortens. So it started out as 109.5, it squeezed into 107, it got even smaller to 104.5. You do not need to memorize these, you just need to call them less than 109.5 and less than 109.5. And that is the summary of the geometries up to 4 legs, 4 legs attached to the central atom, and that's going to be the end of this lesson.